Assalamu alaikum. I welcome you all in the week 4 lectures of internal combustion engines ME215. So today is the last lecture on chapter number 3, air standard cycles and their analysis of book Kennison. These are the learning outcomes of today's lecture. In today's lecture, we will study the dual cycle. We will derive the expressions of thermal efficiency, work output, and mean effective pressure of the air standard dual cycle. Then we will do the problem-based learning of the air standard dual cycle. In the last, we will discuss very briefly the Britten cycle, and we will do a short comparison of Otto, diesel, and dual cycles. So, if you remember, in the last classes, we discussed the Otto and diesel cycles, and what we did, we first derived the expression for thermal efficiency, net work output, and mean effective pressure. So we will do the same thing for the dual cycle. That is, we will first do the derivation part, and then we will do the numericals. These are the TV and TS diagrams. 1 to 2 is isentropic compression. In dual cycle, as the name suggests, there will be both constant volume heat addition and constant pressure heat addition. So 2 to 3 is constant volume heat addition, 3 to 4 is constant pressure heat addition, and is 4 to 5 is constant isentropic expansion process. 5 to 1 is constant volume heat rejection. So dual cycle is another idealized cycle of an actual engine. So students, please note that Otto cycle and diesel cycle, they do not exist in reality. Actually, they are the approximation of actual engines. So when the diesel and dual cycle, Otto and diesel cycles were presented and discovered by the scientists, uh, someone thought that we can also approximate the actual engines with an idealized cycle in which we have both constant volume and constant pressure heat addition. So it was thought that it would be a better approximation of the actual engines. So 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 1. In the TS diagram, these processes are also shown. 1 to 2, constant isotopic compression, as entropy remains constant and temperature increases. 2 to 3, constant volume heat addition, and 3 to 4, constant pressure heat addition. And students, please, you can note that the temperature rise during 2 to 3 is greater than the temperature rise during process 3 to 4. The reason for this behavior is that uh, I think the arrows are wrongly put, so the arrows should be clockwise. So 2 to 3 is constant volume heat addition. So there will be no work done. So all the heat will be used to bring the temperature rise of the working fluid. So that is why the temperature rise is higher in during the process 2 to 3. But during the process 3 to 4 is a constant pressure heat addition process. So during this process, work will also be done. So some heat which is provided to the working fluid will be used to do the work done. So the temperature rise will be lower. So this is the scientific reason this may be asked in the examination. So I can show you the picture where this effect is shown more visibly. So the picture is heavy. It is taking time for the opening. Okay, so you can see here that this is the PV and TS diagram for the dual cycle. So the temperature rise during the process 2 to 3 is higher than the temperature rise during the process 3 to 4, and the arrows are in the clockwise direction. This is the real diagram. So let's move forward. So let's first write the thermal efficiency expression. So efficiency formula is net work output divided by Q in. Work net can also be written like Q in minus Q out divided by Q in. And the expression can be simplified as 1 minus Q out upon Q in. This is equation number 1. Now Q out will be U5 minus U1, which can be written as MCV T5 minus T1. Now there will be two Q in. Q in during constant volume heat addition, which will be U3 minus U2, MCV T3 minus T2, and Q in during constant pressure heat addition, which will be H4 minus H3, and which can also be written as MCP T4 minus T3. So total Q in will be Q in during constant volume heat addition plus Q in during constant pressure heat addition. So this thing is written here, 1 minus Q out. Q out is MCV T5 minus T1, and Q in is MCV T3 minus T2 plus MCP T4 minus T3. We can take MCV constant or MCV common. So MCV will be cancelled out. So T5 minus T1, T3 minus T2, Cp upon Cv, because we have taken Cv common, so Cv was not here, so it should become Cp upon Cv, and Cp upon Cv is K. So let's call it equation number 2. Now we will follow the same approach which we adopted during the derivation of thermal efficiency of diesel cycle. That is, we bring all the temperatures in terms of compression ratio, K, cutoff ratio, and pressure ratio. So we know that during process 1 to 2 is isentropic compression, so we can use the isentropic relation T2 upon T1 is equal to V1 upon V2 to the power K minus 1. V1 upon V2 is actually R compression ratio, so T2 can be written as T1 R to the power K minus 1. So we have represented T2 in terms of T1 R and K. Now let's use the process 2 to 3, which is constant volume heat addition. We can apply the ideal gas relation P2 V2 upon T2 is equal to P3 V3 upon T3. V2 and V3 will be cancelled out because volume is constant. So T3 upon T2 will be equal to P3 upon P2, and P3 upon P2 is actually pressure ratio, which we discussed in the Otto cycle. So T3 will be equal to T2 RP, and T2 we calculated in terms of T1 R to R and K. So we can put the value of T2 here, T1 R K minus 1 RP. So T3 is also represented in terms of T1 R K and RP. Now let's consider process 3 to 4, which is constant pressure heat addition. We can apply the ideal gas relation P3 V3 upon T3 is equal to P4 V4 upon T4. P3 and P4 will be cancelled out because pressure is constant. T4 upon T3 will be equal to V4 upon V3, and V4 is volume after constant pressure heat addition divided by V3. V3 is volume before constant pressure heat addition. So V4 upon V3 is actually cutoff ratio. So T4 will be equal to T3 into RC, and T3 is this. So we can put the value of T4 is equal to T1 R to the power K minus 1 RP RC. Now let's consider process 4 to 5. We can apply the isentropic relation T5 upon T4 is equal to V4 upon V5 to the power K minus 1. Now please note, this thing will also be used in the derivation of the network output V4 upon V5. Now V5 upon V3 is compression ratio. How? V5 will be equal to V1 and V3 will be equal to V2. If we see the TS and PS diagram, TS and PV diagram. So V5 is actually and V3 is actually equal to, so V5 upon V3 is equal to V1 upon V2 is equal to R. Now V5 will be equal to RV3. So we can put V5 is equal to RV3, and V4 upon V3 is RC. So V4 upon V5 will become RC upon R. Now T5 will be equal to T4 Rc upon R to the power k minus 1. We can put the value of T4 which we have already derived. So R to the power k minus 1, R to the power k1 will be cancelled out. Rc and Rc into Rc to the power k minus 1 base is same, power will be added. So it will become Rc to the power k. So T5 is represented in terms of T1, Rp and Rc. Okay, Rc. So now we can put the values of T2, T3, T4 and T5 in equation number 2. Here we can take T1 common, T1 will be cancelled out. Then we can do the simple mathematics and we can get this expression of the dual cycle thermal efficiency. You can see that we have an additional parameter Rp, and Rp, what will it do? Rp is also in numerator and also in denominator, so actually its effect will be more dominant in the denominator, uh, and it will actually cause this factor to be such that the efficiency of the dual cycle will be in between the efficiency of the Otto and and diesel cycle. So this thing you can confirm by doing a simple calculation in the Excel sheet. If you remember in the thermodynamics course, I taught you to how to do the soft calculation in the Excel, in the Microsoft Excel. So you can take the formulas for the thermal efficiency of Otto, diesel and dual cycles, and then you can take the random values for Rp, R, Rc and K, and then you can change the values and see the effect. So if you take the normal values, and then you will see that the efficiency of the dual cycle will be in between the efficiency of Otto and diesel cycle if you take the same values for R and the other parameters. So if, and in this expression if you put Rc is equal to 1, then it will become Otto cycle, and if you put Rp is equal to 1, then it will become diesel cycle. So you can check this thing by putting the values of Rc is equal to 1 and Rp is equal to 1. Okay, so now let's come to the second part, second derivation, that is the work output. So in dual cycle, we can find the work output as area under process 3 to 4 plus area under the process curve 4 to 5 minus area under the process curve 1 to 2. So this thing I also explained during the diesel and Otto cycle work output derivation. So let's move forward. Uh, P3 V4 minus V3 plus P4 V4 minus P5 V5 divided by K minus 1 minus P2 V2 minus P1 V1 upon K minus 1. So if you look at the figure PV diagram, 2 to 3 there will be no work done because it is a constant volume heat addition process, so the moving boundary work will be 0. 3 to 4 we will have the moving boundary work, so pressure P3 will be equal to P4. So P3 V4 minus V3 plus P4 V4 minus P5 V5 divided by K minus 1 minus P2 V2 minus P1 V1 divided by K minus 1. So this is the expression. So you can do it by yourself as well. Now we can take K minus 1 LCM. So P3 V4 minus V3 will be multiplied with K minus 1 and the rest will be same. We can take P1 V1 common. So P3 V4 divided by P1 V1 minus P3 V3 divided by P1 V1 whole multiplied by K minus 1. P4 V4 divided by P1 V1, P5 V5 divided by P1 V1, P2 V2 divided by P1 V1, and P1 V1 will be common. So plus 1 will be left, minus minus plus. Now let's call it equation number 1 and simplify the individual terms. So let's start with P3 V4 upon P1 V1. So P3 upon P1 V4 upon V1 can be written as P3 divided by P2 multiplied by P2 upon P1. So we have multiplied and divided by P2. V4 upon V3 multiplied by V3 upon V1. So we have multiplied and divided by V3. So now by doing this thing we can see that P3 upon P2 is actually Rp, P2 upon P1 is actually R to the power K, V4 upon V3 is cutoff ratio, and V3 upon V3 is actually V2, and V2 upon V1 is inverse of compression ratio. So we can simplify this thing as Rp Rc R to the power k minus 1. The next term is P3 V3 upon P1 V1. So P3 V3 upon P1 V1 can be written as P3 upon P2 multiplied by P2 upon P1 multiplied and divided by P2 V3 upon V1. So P3 upon P2 is Rp, P2 upon P1 is R to the power k, V3 is V2, V2 upon V1 is inverse of compression ratio. This thing can be simplified as Rp, R to the power k minus 1. Next term is P4, P1 V1. This thing can be written as P4 upon P3 multiplied by P3 upon P1, V4 upon V1. So P4 and P3 are constant, this will be cancelled out. P3 upon P1, V4 upon V1, this is actually we have already done. P3 upon P3 V4 upon this thing simplified to Rp Rc R to the power k minus 1. So this thing we have already done, so there is no need to do it again. So we can write directly Rp Rc R to the power k minus 1. The next term is P5 V5 upon P1 P5 V5 upon P1 V1 can be written as P5 upon P4, P4 upon P3, P3 upon P2, P2 upon P1. So like we have multiplied and divided by P4, P3 and P2. So P2 will be cancelled out, P3 will be cancelled out, P4 will be cancelled out, and we will be left with P5 upon P1, which is actually the initial quantity. So and V5 and V1 are same. V5 is equal to V1. So this thing will be cancelled out. So P5 upon P4 can be written as V4 upon V5 to the power k, which we did in the derivation of thermal efficiency as well, and we saw that it came out to be Rc upon R to the power k. P4 is equal to P3, so P3 will be cancelled out. P3 upon P2 is Rp, P2 upon P1 is R to the power k. So this thing can be simplified as Rc. This thing can be simplified as I think this is something wrong. So R to the power k will be cancelled out. So it will be Rc to the power k into Rp. So this k should be here. This is a typo mistake, and I have checked uh, this thing is corrected in the later part. P2 V2 upon P1 V1 can be written as P2 upon P1 is R to the power k, and V2 upon V1 is inverse of compression ratio. It will be R to the power k minus 1. Now we can put all these values in equation number 2. Then we can do the simple calculation, like we can multiply k with this and then minus 1 with this, and then this term will be cancelled out. Then we can do simple mathematics and rearrangement and the common things, and then we will be left with this expression. So let's check whether we have put Rc Rp to the power k. This is here Rc to the power k Rp. So this thing is correct. Okay. Now let's derive the mean effective pressure. So mean effective pressure is work output divided by swept volume. Work output we have just derived. Swept volume can be written as V1 minus V2 can be written as V1 minus V1 upon R. V1 can be taken common. 1 minus 1 upon R. V1 will be cancelled out. We can take LCM. It will become R minus 1 upon R. R will come in the numerator. P1 R divided by k minus 1 R to the power R minus 1, and the same expression. Okay, so if you are asked in the exam to derive the mean effective pressure, so you have to derivation of net work output, then you can derive the mean effective pressure expression. It is not like this, that if you have memorized the net work output expression and then you just put it here. No, been asked to derive the mean effective pressure expression, then you have to start from here, and there is no need to do the thermal efficiency derivation. For mean effective pressure, you have to start from the work output derivation. Okay, so now these things are done. Let's start solving the numericals. An oil engine works on the dual cycle, the heat taken in at constant pressure being twice that of the heat taken at the constant volume. So heat addition at constant pressure is twice of the heat taken at constant volume. So Q in P constant will be 2 times Q in volume constant. The compression ratio of the engine is 8 and both processes follow the law PV to the power 1 minus 1.3 constant. So this is a polytropic process with a polytropic constant of 1.3. The pressure and temperatures at the beginning of compression are 1 bar and 27 degrees Celsius. Determine the air standard efficiency. The mean effective pressure. The expansion ratio is 5.3. So let's start solving this numerical. So using ideal gas equation, P1 V1 is equal to RT1. Pressure is 1 bar is given, so we need to put pressure in kilopascal, so it will be 1 exponent 2, that is 100, because R is in kilojoules, that is why we need to put pressure in kilopascal. So 1 exponent 2 multiplied by V1, 0.287 is R, temperature is 300 Kelvin, so we can calculate V1, and V1 is equal to V5. V1 is equal to, compression ratio is given, V1 we just calculated, so we can calculate V2. Now V2 is equal to V3, and V2 and V3 to clearance volume, because this is the top dead center, and the volume in the cylinder at top dead center is actually clearance volume. So V2 is equal to V3 is equal to Vc. Similarly, compression expansion ratio is given, which is V5 upon V4. V5 upon V4. V5 we just calculated, so we can calculate V4. So we know the volumes at all the salient points. Now we can calculate the cutoff ratio. Cutoff ratio is V4 upon V3, and cutoff ratio is coming out to be 1.509. We can also represent all the volumes in terms of clearance volume. V1 is equal to V5 is equal to RVC, because V1 upon V2 is R, V2 is actually Vc, so V1 will be equal to RV2, RVC. V2 is equal to V3 is equal to Vc, V4 is equal to RC V3, and V3 is actually Vc. Now consider process 1 to 2, which is isentropic compression, and in fact in this process it is polytropic compression, so we will use V2 upon V1 to the power n minus 1. N is 1.3, R is 8, we can easily calculate T2. Similarly, we can calculate P2 by using the ideal gas relation uh, on the process 1 to 2. T1 V1 upon T1 is equal to P2 V2 upon T2. So V1 upon V2 is compression ratio, T2 is known, T1 is known, P1 is known. So we can calculate P2. Now we have given that Q in at constant pressure is 2 times Q in at volume constant. We can put the values Cp T4 minus T3, 2 Cv T3 minus T. Now T4 is also unknown, T3 is also unknown. So we can call it equation number 1. We can derive another equation by using the ideal gas relation on process 3 to 4. P3 V3 upon T3 is equal to P4 V4 upon T4. Pressure will be constant during the process 3 to 4. P3 P4 will be cancelled out. T4 upon T3 will be equal to V4 upon V3. V4 upon V3 is actually cutoff ratio. So we have another equation in terms of T4 and T3. So if we can solve equation number 1 and 2 simultaneously to know the values of T3 and T4. Now we can apply the ideal gas relation on process 3 to 2 to calculate the P3. Once we know the P3, we can know also P4, because P3 and P4 will be equal. Now consider process 4 to 5, which is polytropic expansion. We can use this relation to calculate T5 and P5. Here V5 upon V4 is expansion ratio which is given. Now we can calculate the net work output by using this formula. We know pressures at all the points, and we have put all the volumes in terms of clearance volume. So we can calculate the net work output in terms of clearance volume. Clearance volume is known, so we know the net work output. So if R is 1 plus Vs upon Vc, with this equation we can find the swept volume. So we can divide the net work by the swept volume to know the mean effective pressure. Similarly, we can calculate the efficiency, which is net work output divided by Q in. Q in is Cv T3 minus T2. plus Cp T4 minus T3, T3, T4, T2, so all are known. We can know the Qin. So we can divide the expression 374.88 and the efficiency is coming out to be 56.01. Now students, you must be wondering that why we use this long formula to calculate the network output. We could have calculated the network output by calculating the Q in. Here we have calculated Q in. We could have also calculated Q out. Then Q in minus Q out will be network output. So the thing is that we cannot use this approach in this numerical, because the problem is that the compression and expansion are polytropic, and you know that uh, in the ideal cases the compression and expansion processes are adiabatic, uh, sorry, the isentropic. And isentropic, what is isentropic process? Isentropic process is reversible adiabatic process. So isentropic means adiabatic means no heat transfer. But since this is not isentropic, this is polytropic, so there will be some heat transfer taking place during this process 1 to 2 and 4 to 5. Are you getting my point? So my point is that normally in the idealized cycles, the compression process is isentropic, and also the expansion process is isentropic. Isentropic means adiabatic. Adiabatic means no heat transfer. So we we are safe. But in this numerical, 1 to 2 is polytropic compression and 4 to 5 is polytropic expansion. So there will be heat transfer taking place during these processes. Now 1 to 2, now it will be Q in or Q out. Now when you compress anything, when you compress gas, it becomes hot, and heat always flows from high temperature to low temperature. So there will be Q out during process 1 to 2. Similarly 4 to 5, 4 at point 4 the temperature will be maximum, there will be the air will be hot. So again the heat will flow from high temperature to low temperature, that is heat will flow from system to surrounding. So process 4 to 5 will also have the heat out. So I have made a slide for this thing. Okay, so now you can see here that if compression and expansion processes are polytropic, then heat transfer will also occur during these processes. Heat will be lost to surrounding during both these processes, so Q out should be modified, and these two additional heat transfer should be added in Q out to calculate the correct efficiency. So what we are saying that normally if 1 to 2 is isentropic and 4 to 5 is isentropic, so Q out will be only one thing, like only the Q out will be taking place only in during the process 5 to 1. 5 to 1 is constant volume heat rejection, let's call it Q51. So Q51 is the heat rejection, that is Q out. If 1 to 2 is isentropic, 4 to 5 is isentropic, that's enough. So we can only calculate Q out as Q51, that is the heat out during the process 5 to 1. But if 1 to 2 is polytropic and 4 to 5 is polytropic, so we need to consider these Q out as well. Q21 is the heat out during the process 1 to 2, and Q45 is heat out during the process 4 to 5. So now there will be 3 Q out, and if we want to calculate the efficiency, the correct efficiency, we need to modify the Q out. The Q out will be the addition of these three Q out, Q21 plus Q51 plus Q45. Then you will get the total Q out, and then this total Q out should be used in calculation of the work net. So you will get the correct work output. So let's look at the method 1. Now this numerical can be solved uh, by method 1, where efficiency will be calculated on the basis of net work output divided by Q in, but you will calculate the net work output by using the mean effective pressure. So mean effective pressure multiplied by swept volume will give you the net work divided by Q in, and mean effective pressure should be calculated with this formula. When you use this formula, actually you have you have taken the actual values of pressures at all the points and actual values of of the volumes at all the points. So you have implicitly taken into account the effect of the polytropic processes. So this method will give you the correct efficiency, the correct work output, or the actual work out of this cycle. So in the method 2, if you use this formula, efficiency 2, if you calculate the efficiency 2 by this formula, then this efficiency will be wrong, because in the derivation of this formula, if you recall, you only considered this q out. You did not consider q45 and q21 in the derivation of this formula, this expression. You can go back in the earlier part of this lecture, and you can see that in the derivation of thermal efficiency of dual cycle, and when we derived this formula, we did not consider the heat rejection during the during the compression 1 to 2 and expansion process 4 to 5. So this will give you the wrong efficiency for this problem. So eta 1, which you calculated with this method, eta 2 you calculated with this method, they will not be equal. Now, third method. In third method, you calculate the efficiency by net work output divided by Q in, and net work will be 1 minus Q out upon Q in, and Q out, for Q out you only considered Q51 divided by Q23 plus Q34 for Q in. Here you can see that you have only considered this Q out. Then again this formula will give you the wrong efficiency, and this will not be the correct efficiency. But if you use this method number 4, 1 minus q out upon q in, where q out is calculated by q21 plus q45 plus q51, this is the actual q out, then you will get the correct efficiency. And with this method 4, the efficiency will be equal to the efficiency calculated in the method 1. So method 1 and method 2 are the correct methods to calculate the efficiency for this type of numerical, where the 1 to 2, the compression is polytropic compression and expansion is polytropic expansion. If you for the polytropic compression and expansion, if you use this formula, this is wrong. And if you use this formula where you only considered q out here, then this will also be wrong. Now, what about method 1 and method 2? Method 4 will be very lengthy, because in order to calculate Q21, you need to do the energy balance which you did in the thermodynamic course. Like you need to do the energy balance for process 1 to 2, then you will get Q21. Then you will need to do the energy balance for Q45. You need to use the property tables and everything, and then this method will become very lengthy and cumbersome. So it's easy to use method number 1. So that is why we have used this method in the here. Like we first we calculated the network output by using this formula, and we use this formula, this network output, to calculate the efficiency. So this is the correct method. I hope you have understood. So this thing we can further discuss in the live session or in the WhatsApp group. If you have any query, you can ask. Because in the video lecture I have limited time, so I cannot put too much time to explain all these things. Okay, we can further discuss it in the live session or in the WhatsApp group. So we can skip this numerical. We can straight come to the question number 3a, which I gave in the 2018 final paper. So this is the question. The swept volume of an engine working on dual cycle is 0.0053 meter cube. The swept volume is given, and clearance volume is 0.0035 meter cube. The maximum pressure in the cycle is 65 bar. Fuel injection ends at 5% of the stroke. The pressure and temperature at the start of the compression are 353 Kelvin and 0.9 bar respectively. Determine the air standard efficiency of the cycle. Okay, so let's solve this numerical. So compression ratio is V1 upon V2. V1 is swept volume plus clearance volume divided by clearance volume. V2 is actually clearance volume. Now swept volume and clearance volume both are given, so we can easily calculate the compression ratio. Now cutoff ratio is V4 upon V3. If you see the If you see the PV diagram, volume after constant pressure heat addition is V4 divided by volume before constant pressure heat addition is V3. Now V4. Now V4 we can calculate with this statement. Here it is fuel injection ends at 5% of the stroke. So V4 will be equal to V3 plus 0.05 of the swept volume. 5%. Okay. So V3 plus 0.05 plus into swept volume. So with this we can calculate the cutoff ratio. Swept volume we know, clearance volume we know, because V3 is equal to clearance volume. So clearance volume is also known, so we can calculate the cutoff ratio. R is known, cutoff ratio is known. P2 upon P1 is equal to V1 upon V2 to the power K. R is known, P1 is given, so we can calculate P2. And once we know the P2, P3 is given, so P3 upon P2 is Rp. So we need all these parameters. We needed R, Rc, Rp, and K. We know all these things, and we can use this formula to calculate the dual engine efficiency. Question number 4. An air standard dual cycle has a compression ratio of 9, bore of 250 mm, stroke of 300 mm. The pressure and temperature at the beginning of compression are 1 bar and 303 Kelvin. The maximum pressure is 60 bar. The fuel cutoff occurs at 4% of the stroke. Cp, Cv, K and R are given. Determine pressure and temperature at all salient points, cutoff ratio, thermal efficiency and power output for 3 cycles per second engine speed. So simple numerical. Since stroke is given, bore is given, we can calculate the swept volume by using this formula, pi by 4 d square into L. Swept volume is known, clearance volume is known. We can calculate the compression ratio with this formula, 1 plus Vs upon Vc. V2 is equal to V3 is equal to Vc. This thing you already know. V1 is equal to V5 is equal to Vc plus Vs. Swept volume plus clearance volume is the total volume, which is equal to V1 is equal to V5. Now we can use the isentropic relations to calculate P2 and T2. The ideal gas relation to calculate T3. P3 is equal to P4 given. Cutoff ratio will be found with the help of, because it is given that the fuel cutoff takes place at 4% of the stroke. So Rc will be equal to V4 upon V3, and V4 is equal to V3 plus 0.04 Vs divided by V3. So cutoff is known. V4 can be calculated V3 plus 0.05 Vs. This thing should be 0.04. This is a typo mistake. You can check. Similarly, we can calculate, once V4 is known, we can use the ideal gas relation on process 3 to 4. P3, P4 will be cancelled out. T4 is known. V4 and V3 are known, so T3 can be calculated. P5 and T5 can be calculated using the isentropic relation on process 4 to 5. Q in can be calculated with this formula, Cv T3 minus T2 plus Cp T4 minus T3. Q out can be calculated with this formula, Cv T5 minus T1. Efficiency will be 1 minus Q out upon Q in. We can calculate the total mass because we know the V1. So MT will be 0.0189 kilogram. So this formula we also use in the Otto cycle. Net, its unit is kilojoule per kilogram, so we need to multiply the total mass. So kilogram will be cancelled out, it will be kilogram, it will be kilojoule, multiply by 3 cycle per second was given. So we can also write directly 3 here. So 3 has a unit of cycle per second, so kilojoule per second is kilowatt, so this thing was required. So power is 51 kilowatt. We can move forward. An oil engine working on dual combustion cycle has diameter of cylinder 20 cm, bore given, stroke is given 40 cm, the compression ratio is 13.5. Explosion ratio, that is the expansion expansion ratio, is 1.42. Cutoff occurs at 5.1% of the stroke. Calculate air standard efficiency. Take K is equal to 1.4. So it's simple numerical. Sweat volume can be calculated with the formula pi by 4 d square into L. D is given, L is given, sweat volume can be calculated, R can be calculated, no, R is given, clearance volume can be calculated with this formula, R is equal to 1 plus Vs upon Vc. R is given, Vs just calculated, so we can calculate Vc, V2, V3, they all will be equal to Vc. Cutoff occurs at 5.1% of the stroke, so V4 will be equal to V3 plus 0.051 into Vs. So with this we can calculate V4 because V3 is known. V3 is actually clearance volume. So cutoff ratio will be V4 upon V3. We know cutoff ratio, we know the compression ratio, we know the pressure ratio as well. Pressure ratio is 1.42. Okay, so explosion ratio is actually the pressure ratio. Explosion ratio is actually the uh, pressure ratio, not the expansion ratio. So we can put the values and we can get the efficiency. An oil engine working on dual combustion cycle has a bore of 25 centimeters, stroke of 35 centimeters. The clearance volume is this. Cutoff takes place at 5% of the stroke. The explosion ratio is 1.4. The air standard efficiency of the engine is this. So this is a similar numerical. You can do it on your own. This thing we have already discussed. Okay, so now let's come to the Brayton cycle. In the Brayton cycle, actually we have four components. This is the compressor. Then we have a heat exchanger where the let's suppose in the compressor we take air from the surrounding. That is, we take the fresh air. Compressor compresses the air. Then the high pressure air comes in this heat exchanger. Here heat is absorbed, so it will become hot air, and then this hot and pressurized air will go in the turbine. It will strike with the turbine blades, and the turbine blades will rotate the shaft, so we will get the power output. Then it will go into the heat exchanger. In the heat exchanger, it rejects heat to the surrounding to come at the initial temperature, and then it will go into the compressor, and the cycle goes on. So this is the normal working of a of a Brayton cycle. We have two types of Brayton cycle. One is the closed cycle. This is the closed cycle Brayton cycle, which is normally used in the power production or power generation, and this is the open cycle Brayton cycle, which is normally used in the aeroplanes. Like we can see here in the aeroplanes, fresh air is taken into the compressor. Compressor compresses it. So by compressing it, its pressure increases, but its temperature also increases. So this high pressure and moderate temperature air goes into the combustion chamber where fuel is supplied and combustion takes place, and the air becomes high temperature high pressure here. Now these high temperature high pressure exhaust gases goes into the turbine, strikes with the turbine blades, and the turbine rotates, and we get the power output. And then we also have the nozzles, like these high exhaust gases. Some part of the exhaust gases go into the turbine to run the electrical systems, the power system, air conditioning, lightning, lighting systems, and the other power requirement of the aeroplanes. And then the rest of the exhaust gases go into the nozzles where they are expanded, and then like these uh, their velocity is increased, and when these high velocity exhaust gases exit the nozzle, the thrust is produced and the aeroplane moves forward. And after these the exhaust gases will be dumped into the exhaust gases. So it's an open cycle Brayton cycle. But when you need the power generation, you circulate the working fluid in the closed cycle. So we can see here there are four processes in the Brayton cycle. 1 to 2 is isentropic compression. We can approximate this process, the heat addition process, as a constant pressure heat addition process, because we can assume that there is a negligible heat pressure loss in the heat exchanger. So we can assume that it's a constant pressure heat addition process. 3 to 4 is isentropic expansion, and 4 to 1 is also constant pressure heat rejection process. So this is also a heat exchanger, and we can assume that there is a negligible pressure loss, and the heat rejection process is a constant pressure heat rejection. Like you can, if you recall, 1 to 2, if you recall the diesel cycle, so 1 to 2 isentropic compression, same. 2 to 3 constant pressure heat addition, same. 3 to 4 isentropic expansion, same. 4 to 1 is different. In Brayton cycle and diesel cycle, 4 to 1 is different. In diesel cycle, 4 to 1 is constant volume heat rejection, but in Brayton cycle, 4 to 1 is also constant pressure heat rejection. So we can show the Brayton cycle on the TS diagram like this. We can do the efficiency derivation in the same way. W net upon Q in 1 minus Q out upon Q in, equation number 1. Now Q in will be equal to H3 minus H2, because it's a constant pressure heat addition, so it will be H3 minus H2, which can be written as MCP T3 minus T2. Q out will also be H4 minus H1, not U4 minus U1, H4 minus H1, so it will be MCP T4 minus T1. We can put the values of Q out and Q in here. T1 and T2 can be taken common. Then we can use the isentropic relations of these isentropic relations. T2 upon T1 is equal to P2 upon P1 to the power K minus 1 upon K. This is the third isentropic relation which you derived in the thermodynamics entropy chapter. P2 upon P1 is actually Rp, so it will be Rp to the power K minus 1 upon K. Process 3 to 4 is also isentropic, so T3 upon T4 will be equal to P3 upon P4 to the power K minus 1 upon K. P3 upon P4 is Rp. Left hand sides are same, so we can compare the right hand sides. T2 upon T1 will be equal to T3 upon T4. We can write T4 upon T1 is equal to T3 upon T2. So this thing will be cancelled out. We will be left with 1 minus T1 upon T2. It can be written as 1 minus 1 upon T2 upon T1. And T2 upon T1 is Rp to the power K minus 1 upon K. So the efficiency of the Brayton cycle depends on two parameters. One is Rp, pressure ratio, and K, the specific heat ratio. We can plot this thing as well, the efficiency of the Brayton cycle like this. Efficiency on y-axis, pressure ratio on x-axis. We can see that if the pressure ratio is increasing, the efficiency also increases. And similarly, if we increase the K, the efficiency also increases. This thing is similar to the behavior which we observed in the Otto cycle. Now let's do a quick comparison of Otto, diesel and diesel cycles. First, do the comparison at same compression ratio and heat addition. So for this, in order to understand this comparison, I would like to mention few points. We know that efficiency formula is 1 minus Q out upon Q in. 1 minus Q out upon Q in. If we increase Q in, efficiency will increase. If heat addition is larger, then efficiency will also be larger. So we can see from this expression. What about Q out? I think I should use the consistent samples. I should have used the consistent samples. Q in. So if we increase Q in, higher the Q in, higher will be the efficiency. And what about Q out? Heat rejection should be low. The lower the heat rejection, the higher will be the efficiency. So Q in efficiency is directly proportional to Q in, and efficiency is inversely proportional to Q out. So heat addition should be as high as possible, and Q out should be as low as possible. So then the efficiency will be higher. Secondly, if we have a TS diagram, so if you recall the thermodynamics, the area under the TS diagram is, let's suppose this is 1 to 2. So area under the TS diagram is heat transfer. So area under the TS diagram is actually the heat transfer. So you can recall and you can go through in the Sangel book and you can see the confirmation about this thing. So if you have, let's suppose, two graphs, two processes, TS. Okay, so one is this process curve 1 to 2, and one has this process curve 1, 2. So which one will have higher heat transfer? This one. The longer the process curve, the higher will be the heat transfer. This makes sense. And shorter the process curve, the shorter will be the smaller will be the heat transfer. So if you remember these points, then it will be very easy to understand these graphs. Now we have to compare the Otto, diesel and dual cycle at same compression ratio and heat addition. So which one has the highest efficiency? So actually in this one diagram you can find all the three cycles. How? You can see that 1 to 2, this is isentropic compression. 1 to 2, 2 to 3, 2 to 3 is constant volume heat addition. 3 to 4 isentropic expansion, and 4 to 1 is constant volume heat rejection. So this is the Otto cycle. So red is actually Otto. Now we have diesel cycle as well. So let's suppose 1 to 2, 1 to 2 is isentropic compression. That is why they have written that it is same compression ratio, because 1 and 2 are same for all the cycles. This is isentropic compression. Then 2 to 3 dash is constant pressure heat addition. 3 dash to 4 dash isentropic expansion, and 4 dash to 1 is constant volume heat rejection. So blue line is actually showing diesel cycle. So diesel cycle is 1 to 2, 2 to 3 dash, and 3 dash to 4 dash, and 4 dash to 1. While Otto is 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Now we also have the dual cycle. So dual cycle is 1 to 2 isentropic compression, 2 to 2 double dash constant volume heat addition, 2 double dash to 3 double dash constant pressure heat addition, 3 double dash to 4 double dash, here it is not written, and 4 double dash to 1. So this is the yellow is actually dual cycle. So now you can see that in one figure uh, all the three cycles are represented, and for all the cycles 1 to 2 is same, and 1 to 2 volume V1 and V2 are same. So it means that all the three cycles have same compression ratio. Now let's look at the TS diagram. 1 to 2, 2 to 3, 3 to 4. This is the Otto cycle. 1 to 2, 2 to 3 dash, 3 dash to 4 dash to 1. This is diesel cycle. 1 to 2, 1 to 2, and then 2 to 2 dash, 2 double dash, 2 double dash to 3 double dash, and 3 double dash to 4 double dash into 6 double dash. So this is the dual cycle. So area under the process curve, like from 5 to 2, 2 to 3, 3 to 6. This is the heat addition for Otto cycle. 5 to 2, 2 to 3 dash, 3 dash to 4 dash, and 4 dash to 6 dash. This is the heat addition for the uh, diesel cycle. 5 to 2, 2 to 2 double dash, 2 double dash to 3 double dash, 3 double dash to 4 double dash, and 4 double dash to 6 double dash. This is the heat addition for the dual cycle, and this area is same. So that is why it is given that the heat addition is same. Now you need to find that which cycle will have the higher efficiency. So now efficiency depends on Q in. Efficiency depends on same compression ratio. Efficiency depends on compression ratio, or efficiency depends on Q in, Q out. So Q in is same now. So now let's look at the Q out. 4 to 1. So now you can see that 4 to 1 is the 4 to 1 is the heat rejection of Otto cycle. This is the process curve of heat rejection of Otto cycle. Now 4 dash to 1 is the heat rejection of process curve of diesel cycle, and this is the longest process curve. You can see the red one is the shortest and blue one is the longest, and dual cycle process curve is in between. You can see 4 double dash to 1. So which one will have the highest heat rejection? The diesel cycle will have the highest heat rejection, and Otto cycle will have the least heat rejection. So Q out is smallest for Otto cycle. This thing is written here. You can see here the Q out of Otto cycle is less than Q out of dual cycle, and this is less than Q out of the diesel cycle. So Q out of the diesel cycle is the largest, lowest efficiency. So the Otto cycle will have the highest efficiency because its heat rejection is lowest. So you can see that the process curve of heat rejection of Otto cycle is the shortest. So it will have the lowest Q out. And since I already told you that efficiency is inversely proportional to Q out. Smallest smaller the smaller the Q out, the higher will be the efficiency. I hope you have understood. So now let's move forward. Now same compression ratio and heat rejection. So it is little bit easier because we have only two cycles. Now we have same compression ratio and heat rejection. So you can see that 1 to 2 is same. 1 to 2 is same for both the cycles. 1 to 2, 2 to 3, 3 to 4, 4 to 1. This is the Otto cycle. And 1 to 2, 1 to 2, 2 to 3 dash, 3 dash to 4, and 4 to 1. This is the diesel cycle. So 1 to 2 is same for both the cycles. So this is the same compression ratio, and you can also see here that the heat rejection process curve is same for the both cycles. So heat rejection is same. That is why it is written here. Same compression ratio and heat rejection. Now we have to compare the Q in. So now you can see, now you need to compare the Q in. So this is Q in process curve for Otto cycle, and this is the Q in process curve for diesel cycle. So you can see that this area is additional in the constant volume heat addition process, that is in the Otto cycle. So Q in of Otto cycle is greater than Q in of diesel cycle. I can tell you, like, look, This is the Q in process curve of Otto cycle. So area under this curve will be this, and the for process curve for the constant pressure heat addition, that is the diesel cycle, will be this. So its area will be like this, and it has this area less. So the area, so the Q in of Otto cycle is larger than the Q in of diesel cycle, so it will have higher efficiency. So efficiency of Otto cycle will be greater than the efficiency of the diesel cycle at same compression ratio. This thing we also discussed in the derivation of the thermal efficiency. When we derive the thermal efficiency of diesel cycle, we saw that at the same compression ratio, Otto engine has greater efficiency than the diesel engine. And the second thing you can see here as well, that in constant volume heat addition, temperature is, this is T3, this is T3, and T3 dash is the temperature during the constant pressure heat addition. So constant volume heat addition temperature is higher than the constant pressure heat addition temperature, because the reason for this thing is that if you do the constant volume heat addition, then all the heat will be used to bring the temperature rise of the working fluid. There will be no work done. So that is why T3 is higher. But in constant pressure heat addition, the heat provided will also be used to do the work done. So some heat will be used, some energy will be used um, to do the work done, and some energy will be used to bring the change in the internal energy. So that is why T3 dash is lower than the T3. Now let's do the third case. Same peak pressure, peak temperature, and heat rejection. So now same peak pressure and peak temperature. So you can see that 1 to 2, 2 to 3, 3 to 4, 4 to 1 is Otto cycle. 1 to 2 dash, 2 dash to 3 dash, 2 dash to 3, 3 to 4, and 4 to 1. And they have same peak pressure for the both cycle. Same peak pressure, and we can also see here 1 to 2, 2 to 3, 3 to 4, 4 to 1 is Otto cycle. T3 is the maximum temperature, and 1 to 2 dash, 2 dash to 3, 4, and 1. So they have also the same peak temperature. So the peak pressure, peak temperature is same in both the cycle, and heat rejection is also same. That is, the heat rejection curve is same in both the cycles. So what is left? Q in is left. So we need to calculate, we need to differentiate, we need to analyze the Q in. So which one has the higher Q in? So as you can see that constant pressure process, that is the diesel, will have this much greater heat transfer. So Q in of Otto cycle is less than Q in of diesel cycle. That is why efficiency of Otto cycle will be less than the efficiency of diesel cycle. That is, the efficiency of diesel cycle will be greater than the efficiency of Otto cycle at same peak pressure, peak temperature, and heat rejection. So how will this question be asked in the exam? You will be given this statement. You will be given this statement that at same peak pressure, peak temperature, and heat rejection, which one will have the highest efficiency, Otto engine or diesel engine? And maybe this figure will also be given in the exam. So you need to write only this thing, that since the diesel cycle has higher Q in, so its efficiency will be higher than the efficiency of Otto cycle. So for like, maybe this question will be asked for like 3 or 4 marks, and for 3 to 4 marks you only have to write this thing, then you will get the full marks. And the last case is same peak pressure and heat input. So you can see here, and here you can see that you can need to compare the out. So 1 to 4 is the heat rejection process curve of Otto cycle, which is the largest, and 4 dash to 1 is the heat rejection process curve of diesel cycle. So Q out of Otto cycle will be greater than Q out of diesel cycle, so its efficiency will be less than efficiency of diesel cycle. So Otto cycle has a higher Q out as compared to diesel engine, so its efficiency will be lower than the efficiency of the diesel cycle. Okay, so I think this thing is slightly because it has same peak pressure, so this thing is slightly wrong in the this this thing 1 1 to 2 2 to 3 should be here, something somewhat here, and then it should go something like this, because the peak pressure should be same, na? So they should come at the same point. Right now it's wrong. This 3 dash is little bit higher than the 3. This is wrong figure, na? In actual figure, the figure should be like this: 1 to 2, 2 to 3, 3 to 4, 4 to 1, something like this. Okay. Okay, so this is the end of today's lecture. Students, please note that some students have complained that I'm uploading very long videos. So like this video is like more than 60 minutes duration. But students, you should note that what is the total duration of all the videos. So the total duration of all the videos will be around like 100 minutes, and the one video will be like 30 to 35 minutes long. I think this is fine. So you have noticed that in week 1 I have uploaded only 2 videos. In week 2 I have also uploaded 2 videos. Week 3 I have also uploaded 2 videos. So uh, there are the videos are less in numbers, but they are longer in duration. So but overall you have to look at the total duration of the all the video lectures. They should be around like 100 or 110 minutes. Okay, students, if you have any question, you can ask during the live session or in the in the WhatsApp group. I think this thing will be little bit tricky. You need to understand. You need to put time on it to understand all these things. So if you have any more question, if you have any question, you can ask in the live session or in the WhatsApp group. Okay, so with this, I end today's lecture. Allah Hafiz from my side. See you next time.